Welcome back. So here we are again with our point estimate, our sample proportion of 0.534. Now remember, if we took a different sample of 1,000 people, we'd probably get a different number of them saying they favor the policy, so we'd get a different point estimate. So this we can't just say this is the answer for the population. It's just an estimate. We'd get different estimates with different samples. The question is it likely that we would have gotten this estimate if the null hypothesis is true? If it's not likely that we'd have gotten a sample point, a sample proportion of 0.534, then we're going to reject the null hypothesis. On the other hand, if this isn't out of line with that null hypothesis, then we won't reject that null hypothesis. Okay, and it looks like I've got some space here for us to say some of that stuff in the notes. If it is not likely that we got 0.534, then we should reject the assumption that the population proportion is actually 0.50. In other words, we should reject the null hypothesis. If it is likely, or maybe a better way of saying that is if it's not unlikely, then we will not reject the null hypothesis. Now, to answer the question, we need to know about the probability distribution for p hat. So basically what I need to know is that I need to know it's normal, so I can look things up on the normal, the standard normal table. So we need to know about the probability distribution. Basically, is it normal or approximately normal? So notice that the sampling is random. How do I know that? The example said so. That's how I know. NP times 1 minus P. Well, N is the sample size. That was 1,000. P, the population proportion. Okay, here's where we need an assumption as to what it is. We're assuming that it's 0.5. Remember, that's the null hypothesis, is that P equals 0.5. And then 1 minus P, 1 minus 0.5. That actually works out to be 250, and the point of that is as long as that's greater than or equal to 10 and you have these two things being true, then you can conclude that p hat is approximately normal. So what's number 3? The sample size needs to be 5%, less than 5% of the population. Her sample size is 1,000. That'll be less than 5% of the population, assuming her district contains at least 20,000 voters. So, what we end up saying in this class on this thing is just that, yeah, it seems reasonable that that sample size is less than 5% of the population. So it seems reasonable to assume that that the people selected are independent of each other. Okay, the only calculation in here is this NP1 minus P. That's got to turn out to be greater than or equal to 10. Since all three of these things are true, we get to conclude that p hat is approximately normally distributed with mean. So the mean is going to be the population proportion, which we are assuming is 0.5. Okay, so because the mean is the population proportion, we need to have a number to put in here, and that's where assuming the null hypothesis is true gives you some ground to stand on. It gives you something to work with. Okay, remember, we always assume at the beginning that H naught is true, and in this example, H naught was the statement that P is 0.5. Okay, also the standard deviation for p hat we said was square root of, what was it, P times 1 minus P over N. P is 0.5, we're assuming. 1 minus P, again, we're assuming P is 0.5. Sample size was 1,000. And doing that on a calculator gives 0.016. So I know that p hat is approximately normal. Of course, I don't have a normal distribution table for mean being 0.5 and standard deviation being 0.016. We only have a table for the standard normal, the z table, where the mean has to be 0 and the standard deviation 1. But remember, we have a way of converting this normal distribution to the standard normal z distribution. Okay, so we're going to use that to compute the probability of getting the value p hat greater than or equal to 0.35 under the assumption that the actual population proportion is 0.5. Okay, so here we go. This is the same then as the probability that z is greater than or equal to, and remember how you convert, you take your value, 0.534, subtract the mean, divide by the standard deviation. Okay, that gets you a z-score, which turns out to be 2.15 in this case. And by the way, this number that we get for z, this is called a test statistic. So when the book or the homework says find the test statistic, they mean find this z value. Okay, of course, what we really want is the probability of this z value happening. So we look at the table, our z table. Now, remember the z table actually gives you areas to the left. Okay, so here's my table. And remember, the mean is in the middle, is 0 in the middle. I'm looking for area to the right of 2.15, right? It's a right-tailed test because we're investigating the possibility or the probability of being greater. But our table actually gives us areas to the left. So remember, it's symmetric though, the standard normal distribution. So if I instead look up negative 2.15, the table will give me this area, but it's the same as the area to the right of positive 2.15. All right, so what is that area? Let's see, negative 2.15. Negative 2.15, so 2.1 and 5 is over there, so it looks like 0.0158. So again, the table gave us this area as 0.0158, so that means this area is also 0.0158. And this is the area we want, just that one tail. So let me just put one more picture in here. So what we've determined then is, going back to the p hat, if you looked at the p hat distribution, remember that's approximately normal, although the mean is, what did we say, it was 0.5. Okay, so this is p hat. Now the distribution is affected by, part of the characteristic of the distribution is this mean in the middle. And remember that we got that under the assumption that the population proportion was 0.5. In other words, we assumed that H naught was true. That's what gave us an estimate of what of what p hat is. And so we just looked at the probability of an estimate, or a sample, a point estimate, a sample proportion being at least as extreme off the mean as 0.534. So we got that area and determined that that area was 0.0158. Of course, we had to convert to z's to get that, but that is what we determined using the z table. And this, so what is that? That's 1.58%. That's unlikely. So we reject the null hypothesis, H naught. So again, the way we got this probability was by assuming the null hypothesis was true. We got a very small probability of 0.534, or even worse than 0.534 happening under that assumption. So we're now going to reject the assumption. Let's see. Some terminology. I had mentioned that already, but here it is again. The z-value is called a test statistic. Then that probability that we computed is called the p-value. The p-value is the probability of observing a sample statistic, in other words, point estimate, as extreme or more extreme than the one observed under the assumption that the null hypothesis is true. Now, you may have wondered, I hope you wondered, how we decided that 1.58% was sufficiently unlikely as to cause us to reject H sub 0. I mean, where would the cutoff line for likeliness or unlikeliness be? Well, that's where the level of significance comes in, and I didn't drag that into this example, but in all the upcoming examples we will have a level of significance. So if the p-value is less than the chosen level of significance, so if the probability, in other words, is smaller than whatever we've chosen for the level of significance, then we will reject the null hypothesis. You know, and that's probably a good stopping point. We'll come back then and do another example where we have a level of significance, and so we have a specific number that we're looking for in terms of that probability to make our decision on rejecting or not rejecting the null hypothesis. So I'll see you next time with that example.